Okay, we're going to work on some examples that I said I'd get for you guys this morning. So we're going to try to obtain the power series expansion for a function that looks like this. 7x minus 1 over 3x squared plus 2x minus 1. So we want to have the power series expansion for this particular function, and the key here is going to consider your denominator, and you are going to use partial fraction decomposition, which means we're going to write this as a over plus b over. Remember, we have to factor that denominator. And this is 3x minus 1 times x plus 1. So by partial fraction decomposition, 3x minus 1 down here in x plus 1. So on the right side here, remember we get a times x plus 1 plus b times 3x minus 1, and everything over 3x minus 1 times an x plus 1 here. And this is equivalent to our 7x minus 1 over the 3x minus 1 x plus 1. So this implies we get this characteristic equation here of 7x minus 1 being ax plus a plus 3bx minus b. And so if we combine the terms that are like and factor out that variable x, we're going to get the following here. So remember, a plus 3b is 7. And we can say a minus b will be negative 1 over here. Okay. So we get two equations, two unknowns. I'm going to say to you guys here, we can actually change our signs here, multiply by negative 1, and we can use the what's called the addition method. And by the addition method, we essentially get 4b is 8, or b is 2. And if b is 2, we get a plus 6 is 7, or a is 1. So by partial fraction decomposition, a is 1 and b is 2. So we're going to replace these values, 1 and 2. So essentially the function is equivalent to the following. Uh, 1 over 3x minus 1 plus 2 over x plus 1. Okay, so remember earlier this morning, today, we're going to use the relationship that the function 1 over 1 minus that triangle is the sum of triangle to the nth power n is 0 to infinity. So this is the key to working with both these questions, or both these expansions. So we're going to expand. We're going to look at the power series for the first rational and a power series for the second one. Okay, so let's do them one at a time here. So I'm going to rewrite my denominator for the first power series expansion here as 1 over -1 plus 3x. And the next one will be 2 times 1 over 1 plus x. Okay, so what I'm going to do now is I'm going to factor out down here my denominator. I'm going to factor out a -1. And we get -1, 1 minus 3x. And here we're going to just write this as a 1 minus a minus x. And as you can see now, all together, you should get -1 over 1 minus 3x plus 2 times 1 over 1 minus x. And this portion and this portion, these are in your triangles. So I have a triangle here, using the power series expansion that we talked about here. So we're going to use this kind of expansion here. Okay, so that means I get negative summation 3x to the nth power, n is 0 to infinity, plus 2 summation -x to the nth power, n is 0 to infinity here. So we're going to simplify what we have here by properties of exponents. This is going to be using algebra 3 to the n, x to the n right up in here. And here we're going to have -1 to the n, x to the n. So altogether, I get minus sum n is 0 to infinity, 3 to the n, x to the n, plus 2 summation -1 to the n, x to the n is 0 to infinity. Okay. Now, all we're going to do is use properties here of, summation. And I'm going to rewrite this because I'm going to write this as the positive 2. I'm going to rewrite these terms. You guys are going to see what I want to do with this. So this is -1 to the n, x to the n, minus the summation 3 to the n, x to the n, where n is 0 to infinity. We're going to put those values inside. N is 0 to infinity, 2, -1 to the n, x to the n, minus summation 3 to the n, x to the n. And we're now going to put this under that single summation sign. Okay. Now, as you guys can see, what we can do here is we can factor out the x to the n now. So you're going to be left with this summation here of, starting at 0 to infinity, 2, -1 to the n, minus 3 to the n. This is my constant. And this is now x to the n. Just going to check to see how we want to write this, and that's going to equal to that 7x minus 1. Try to find the original function. And it looks like it was 3x squared plus 2x minus 1. So we have a power series expansion. Now, let's go back over here. Let's consider now the interval of convergence. And remember, we get convergence when, if we go back over here, this thing, the absolute value of 3x has to be less than 1, strictly less than 1. Which means 3 times it, we'll do every detail. Product rule, 3 is positive. Means the absolute value of x has to be smaller than 1/3. So negative 1/3 less than x less than positive 1/3. And that's going to give us convergence right here for this first power series expansion. Now be careful. We have 2 functions here to expand. And the absolute value of negative x now has to be smaller than 1, which is the same as saying the absolute value of x has to be smaller than 1. So in order to have convergence, ladies and gentlemen, I'm going to say we have 2 intervals to consider. Now, we need convergence for both of these series. So in order to have convergence for both series, we need the intersection of these 2 intervals, because it has to satisfy both intervals, the first interval and the second. So the intersection of these 2, we're going to say here, I'm going to leave it this way, is negative 3 less than x less than 1/3. So here's our interval of convergence. And if we want to write that in interval notation, it'll be negative 1/3 less than x less than positive 1/3. And again, we need this to satisfy both criteria, which is why we look for the intersection. Anyway, just yelling at the dog. Okay. So we want to go over another power series expansion that we did earlier today. Let's try something like this. If we had x squared, let's write this function this way. We can write it this way here. X squared over 1 minus 2x in parentheses squared. We're going to have to write this in terms of a power series. Now, I want you guys to recall earlier this morning, because when you want to look at it this way. We got x squared times 1 over 1 minus 2x to the second power here. So this morning, we developed this power series expansion where I have 1 over 1 minus triangle to the second power. And I proved to you, well, this series expansion, I proved to you, n is 0 to infinity, n plus 1, x to the n. So I want to double check if it's 0. It sure is. And this is not x. Well, this is what it was this morning. Okay. And what you really use here, I'll rewrite it. 1 minus triangle now to the second power is that summation 0 to infinity n plus 1 triangle to the nth power. So because we know how to handle this situation, we did this morning, we're going to expand as a power series what you see here. And what's in my triangle now is simply 2x. So if I keep that, let's do that in blue, I guess. So this means 1 over 1 minus 2x squared is simply the sum, n is 0, n plus 1, that's 2x to the nth power. So we identify what's in the triangle down here, and we use this expansion formula. Now, of course, you do a little bit of algebra here, and this becomes 2 to the n, x to the n. So 1 over 1 minus 2x squared, sum n is 0 to infinity, n plus 1, 2 to the n, x to the n. And then don't forget what we had here. We had a factor of x squared that gets multiplied to that. So if I multiply both sides by x squared, we get x squared over 1 minus 2x to the second power. I'm going to distribute. So that means my x squared now is inside, and I'm going to put it next to the n is 0 to infinity. I'm going to put it next to the x term because we're going to do some algebra here. So all we did was distribute here. Okay, remember, this is a sum, so I'm going to distribute. I'm going to multiply that x squared times the sum there. And then you get x to the n plus 2. So the power series expansion becomes sum n is 0 to infinity, n plus 1, 2 to the n, x to the n plus 2. Now, I'm just checking a few things here. And double checking to see everything's okay with this. Yeah. Anyway, if you like, I mean, here's something we can do. Let me write it this way as a solution here for you. Do you want to change the index? I don't know if you want to change that index. You may not. We could change the index if you like, but here's something you might see. If you change the index, you might say, okay, they might do something like that. Let's try this out. There's a couple of things you can see. You can say they're going to let I be what that is, n plus 2. I think the book did this. You can let that be, yeah, you could try that. That's fine. And in that case, then n will be I minus 2 because you just solve for n. And so we're going to do a couple of things. When n is 0, that means I starts at 2 because 0 plus 2 is 2. And now you have n plus 1, 2 to the I minus 2, x to the I. But don't forget that n is I minus 2. So right in here, I'm going to use this relationship for n. So you can say I minus 2 here, which really means you have the summation for I is 2 to infinity. And that's going to be now I minus 1, 2 to the I minus 2, x to the I. And then now you can say, can I change I to n? Yes. And you obtain the summation. N is 2 to infinity, n minus 1, 2 to the n minus 2, x to the n. So here's an equivalent, and I'm getting trapezoids all day long with this iPad. And in the past, I always got all these rectangles. So I don't know, but anyway. Okay, that's another representation you can see here. And here's another example of what you can have. And I could do a third example if you guys like. I could actually do something like this, but I won't. I'm going to leave it as is. So here's another way we could look at this. And again, you could look at the interval of convergence for this as well, based on the work we did earlier. All right, so let's look at another example. Something we did earlier. They want to give you the power series expansion for inverse tangent of 3x now. Or let's do x over 3. Yeah. Inverse tangent here of x over 3. Just trying to see if there's anything in our book that looks anything like this. They do a little bit. They do one inverse tangent of that, but okay. Well, how about if we do this? Inverse tangent maybe of pi x. Yeah. So this morning, we demonstrated that the inverse tangent of x this morning is an alternating series, 0 to infinity, negative 1 to the n. We show this as x to the 2n plus 1 over 2n plus 1. And again, for the absolute value of x being less than 1, I believe. Okay, so what we're going to do now is we're going to remove that x, and we're going to put that triangle like we said earlier. And that's now a triangle here. So what we have inside here is pi x. So this means the inverse tangent pi x is a summation, and it's 0 to infinity, negative 1 to the n, pi x to the 2n plus 1, everything over 2n plus 1. And what we need to know, or we need to have, is the absolute value of pi x has to be smaller than 1 in order to have convergence. So at this point here, we're going to do a little bit of algebra, properties of exponents, and we obtained here some n is 0 to infinity, negative 1 to the n, pi to the 2n plus 1, x to the 2n plus 1, everything over 2n plus 1. And here's your power series expansion for the inverse tangent of pi x. So you might say, well, what about the interval of convergence? Well, when the absolute value of pi x has to be smaller than 1, and that means then the absolute value of pi times the absolute value of x is smaller than 1, or pi absolute value of x is smaller than 1, we get the absolute value of x is smaller than 1 over pi, and our interval of convergence, again, is going to be negative 1 over pi less than x less than 1 over pi. So here's what we get for this power series expansion for inverse tangent of pi x. Now, we're going to go back, and I'm going to say something here about this next example. They want us to do the power series expansion for a natural log of 1 minus x. Now, this morning, I did the natural log of 1 plus x. And let's note where this actually comes from. Okay, we have 1 over 1 minus x. We've seen the power series expansion for this as the summation of x to the n and it's 0 to infinity for the absolute value of x being smaller than 1. Okay. Now, what we're going to do with this, since this is a little bit different from this morning, okay, what we're going to do now is we're going to integrate both sides with respect to dx. Now, on the left, of course, we're going to use u sub, where u here is 1 minus x. So on the left side here, we got the integral of 1 over 1 minus x du, which is really the integral of 1 over u. And this is going to be du is minus dx, or dx will be minus du. So let's be careful. So this will be minus du. And so that's a minus 1 over u du. So I get minus here, natural log absolute value of u, which is minus natural log absolute value of 1 minus x. And that's on the left side. So this becomes minus natural log absolute value of 1 minus x. Okay, on the right side, though, so now we're going to focus on this integral on the right. So the integral of a sum is sum of integrals. So I have minus natural log. We're going to change that to 1 minus x because remember, our values of x are between -1 and +1. So anyway, okay. So what we're going to get here is that constant c plus some integral of x to the n dx. That starts with n is 0 to infinity here. So we get minus natural log 1 minus x is that constant plus the summation of x to the n plus 1 over n plus 1 for n is 0 to infinity. Now, just like we did this morning, what we're going to do is we're going to let c be 0. So if you let c be 0 and you plug in, or let x be 0 and you plug in the value for x being 0, this portion over here becomes minus natural log of 1, which is 0, and this portion over here becomes 0. In other words, the constant c is 0. So I'm showing that minus natural log 1 minus x can be described as the sum x to the n plus 1 over n plus 1, or simply the natural log of 1 minus x becomes minus summation n is 0 to infinity x to the n plus 1 over n plus 1. So I proved or developed another power series based on integration. And then that's good for, this is n is 0, and that's good for the absolute value of x being less than 1. Now, we can change the index again. So I'm going to highlight this and say we're going to let this be I. So you might say if I let I now be n plus 1, and this series is now x to the I over I, and you're going to let n be 0 now. So if n is 0, I starts at 1 now. And then don't forget, you have that negative sign out here. So the negative sign. So you might say, what do you do with this now? We can change the variable I back to n. So we have minus sum n is 1 to infinity x to the n over n. And that's the formula for natural log of 1 minus x here. And we do get that trapezoid. Okay. Okay. Now, again, this is only good for the absolute value of x being smaller than 1. So if I take, for example, here's something your book wants to show you. If you let x be 1/2, and I plug that in here, you get natural log of 1 minus 1/2. I think the book wants you to do that one. So why don't you do natural log 1/2? Yeah, okay. That's minus summation. N is 1 to infinity. X is 1/2 to the n over n. And we get natural log of 1/2, which is still that minus 1 to infinity. I'm going to do some algebra. This is going to give me 1 over 2 to the n times n. And I get here, for natural log of 1/2, I can describe this as minus natural log of 2. So if you have a minus sign and a minus sign here, they can divide both sides by -1. What this means is the natural log of 2 can be described simply as a power series. And this will give you a good estimate of the natural log of 2, because if you really expand this, this is 1 over 2 to the first power times 1, plus 1 over 2 squared times 2, plus 1 over 2 cubed times 3. That goes on forever. It is 1/2 plus 1/8 plus 1/24. We can approximate the natural log of 2 this way. So here's the exact value. And an approximate value could look like this. And you can add the first 3, 4, or 5 terms, and it's a good way you can approximate the natural log of 2. So your book actually goes through a kind of demonstration like that. So I wanted to show you where that came from. And then, by the way, if they said to you, what about this power series expansion? They want you to expand something like this. The natural log of 3 minus x now. Okay, now what you're going to use is what you actually had here for natural log of 1 minus x. You say the natural log of 1 minus x, we just showed, is this minus, starting for n is 1 to infinity, 1 over 2 to the n power times n. So we actually have it over here. Yeah, here we go. Okay, just double checking. No, made a mistake. X to the n over n. Okay. X to the n over n. There we go. And this is good for the absolute value of x being smaller than 1. So what we're really, we have this, we just showed where this came from. We're actually going to use natural log 1 minus, change that x to a triangle. Triangle to the nth power over n, where the absolute value of the triangle has to be smaller than 1. So I'm going to have to consider, how do I write 3 minus x as really, 1 minus x? And I'm going to say to you, you're going to factor out, what do we do with that one? Looks like we're going to factor out a what? Let's see if we can write this way. We could do it a couple of ways, I think. I can write this as 1 plus 2 minus x. Yeah, we're going to write it that way. We're not going to factor. We're going to write it this way. So if you said, if I wrote it this way, yeah, the natural log of 1 plus 2 minus x, where what's in my triangle now is the 2 minus x, minus sum, n equals 1 to infinity, 2 minus x to the nth power over n, where 2 minus x in absolute value is smaller than 1. Natural log of 1 plus 2 minus x, that power series expansion. Yeah, I guess there's no algebra to do here with this one. So let me go back and let me erase this. And show you that we can expand our series this way. So natural log 1 plus 2 minus x is minus summation n is 1 to infinity 2 minus x to the n over n. Now we have to take a look at this situation here, this interval. So we know the absolute value of 2 minus x has to be smaller than 1. Now what I'm going to show you guys here is this absolute value here of 2 minus x is equivalent to the absolute value of x minus 2. So the absolute value of x minus 2 is smaller than 1, which means negative 1 is less than x minus 2, which is less than positive 1. And we can add 2 to the right, left, and middle. So I get 1 less than x less than 3. So here is a power series expansion. We have natural log of 3 minus x. And we can write the interval of convergence this way. Okay. Give you some more examples of this. They may say to us to integrate natural log of 1 minus x over x dx. And they're going to want us to integrate by using a power series expansion. So we're going to expand this with a power series. Notice if you try to integrate this, there's no known techniques to integrate. So I'm going to have to expand this function we see here because there's no techniques that we know. So we're going to use the following, right? If we know the natural log of 1 minus x from the last example is this summation over here. We have that negative sign. We start with n is 1 to infinity, x to the n over n. And so what this means is, under my integral sign, I divide by this x. So we have the natural log of 1 minus x over x now becomes what do we get? And I think there's a c here somewhere. So let's not forget you have that plus c. I keep forgetting that plus c. So you have a constant. So let's make sure the constant's there. Anyway, we'll get that there. This is minus. Trying to get the color blue there. Minus the summation. And is 1 to infinity. This is x to the n over n. Don't forget, divided by that x. And then we're going to have that constant out here that we're going to add. And this is really negative sum n is 1 to infinity. X to the n over nx. And then using your algebra here, we're going to get the following summation. Okay. So I got the power series expansion for this function. Now, they want me to integrate here. So that means the integral of the natural log of 1 minus x over x dx is minus, let's do the integral sign here. We're going to say this is going to give us a c minus the integral of the sum x to the n minus 1 over n dx. Integral of a sum is sum of integrals, so I have to integrate really x to the n minus 1, and I'm going to actually, this is n dx. I'm going to actually pull out my constant for this integral, but I'm going to keep it in the summation. So I have my sum, 1 over n. Now we integrate x to the n minus 1 dx. And let's not forget, this is n is 1. 1. And we could just even put 1 here. So here's where my integration occurs. And you might say, okay, what happens here? Well, what happens here? This becomes, by power rule, x, so this is n minus 1 plus 1 over n minus 1 plus 1, or this is x to the n simply over n. So this portion is x to the n over n. I get c minus the summation 1 to infinity, 1 over n times x to the n over n. So I get the constant minus the summation 1 to infinity x to the n squared. So this is the integral of the natural log 1 minus x over x dx. So we found a way to integrate here. And remember, this is good for the absolute value of x being less than 1, or 1 is between, x is between -1 and +1. So we have our interval of convergence, and we have a way to actually integrate this. Okay, we're going to do one more here. See what looks good. Yeah, we're going to try this one here. How about if we try, they're going to want us to do the following. We're going to use some calculus again here. It wants to integrate the inverse tangent of x squared dx. Right? But we can't integrate inverse tangent of x squared. We're going to use a power series expansion to integrate. And remember, we know inverse tangent of anything we already proved. If we go back here, there's an inverse tangent function. There we go. We're going to use this, where it's alternating, and it's a base to the 2n plus 1 over 2n plus 1. Okay. And I believe that's n is 0 to infinity. Okay. And it's no longer x. It's the base there. So inside here, you got x squared. So I'm going to replace this with an x squared here. So here's what we get. And just doing a little bit of algebra, I get x to the 4n plus 2 now. So let me go back here. 4n plus 2, we're going to multiply. Right, we're going to take this power 2 times 2n plus 1. And then this is going to be over 2n plus 1. So at this point, remember, the whole idea is for us to actually take this function and integrate. So we're going to integrate this. And I guess we're going to just, we're going to integrate this here. Don't forget to put the plus c. So on the left side, we integrate inverse tangent x squared dx. The integral of a sum is sum of integrals. So sum integral -1 to the n x to the 4n plus 2 over 2n plus 1 dx plus the constant. Okay. Now, properties of integration again. I'm going to pull out constants here. So I get -1 to the n over 2n plus 1 here, integrate x to the 4n plus 2 dx. So I pulled out these constants here, -1 to the n and 2n plus 1. They're out, and then I just have to integrate right here. And by the power rule, we get x to the 4n plus 3 over 4n plus 3. So here's what the power series expansion looks like. Don't forget to add that constant. So I thought I'd give you a few extra examples today, just looking through my notebook here to see if anything interesting pops out. Nothing very interesting pops out here. I believe this is the absolute value of x needs to be smaller than 1. And in this case, it's the absolute value of x squared. Well, that's positive. And let me do it in red since I've been doing that in red, I guess, at least earlier today. Absolute value of x squared needs to be smaller than 1, which is the same as saying x squared is smaller than 1 because it's positive. And then by sign analysis, what we talked about this morning, this is the interval they're talking about. So we can integrate by power series expansion. So here's some examples for you guys, and I'll upload them to YouTube.